Welcome to Lesson 6 of GPS course, and this time we'll be talking about two coordinate systems and have a little bit of discussion concerning heights. We've touched on that a little bit. Now these coordinate systems that we're going to discuss are plane coordinate systems based upon the fiction that the Earth is flat, which of course immediately introduces distortion. However, much of GIS work and GPS work as well is done based upon this presumption. So it is worthwhile to spend some time discussing how the distortions are handled and some of the elements. So we will be talking about state plane coordinates and universal transverse Mercator coordinates, both plane coordinate systems. And we'll be discussing ellipsoidal heights and geoidal heights and orthometric heights. Plane coordinates persist. They are convenient. The calculations can be done with plane trigonometry, and they are ubiquitous. GIS coordinate systems typically are plane, state plane coordinates being used a great deal in United States and North America in general. Also, universal transverse Mercator coordinates adopted by NATO and the military and civilian organizations worldwide for various mapping needs. Here we have on this slide, and we'll talk more about this in a bit, the Lambert conformal conic projection on the top and the transverse Mercator projection on the bottom. Both rely on expressing the coordinates in X and Y, northings and eastings, of course the Y being the northing and the X being the easting, and they're both based upon the fundamental assumption that we're dealing with a flat surface, which of course we're not. Of course, as long as the extent of the coverage of the coordinate system is limited, the curvature aspect, while it leads to distortion, can be managed. It's when the flat map, the flat coordinate system, extends beyond a limited area that the distortion can, of course, get out of hand. Also, the seams, if you will, between zones of coordinates can be troublesome as well. State plane coordinate systems are based upon map projections, and this, of course, means projecting a portion of the Earth's surface onto a plane, and those planes need to be developable, meaning that if they are split up an element, they can be flattened. And you see an example here of two developable surfaces, a cylinder and a cone. The cylinder being used in Mercator and transverse Mercator, and the cone in Lambert conic, which are the two that are most common in state plane coordinate systems. Of course, there is one oblique portion of state planes. That's the panhandle of Alaska. The problem, as I say here, is often illustrated by trying to flatten part of an orange peel. If the orange peel stands in for a part of the surface of the Earth, a small part can be pushed flat without too much deformation. But when the portion gets large, flattening it inevitably leads to tears and stretches and a distortion. And this, of course, is synonymous with what happens with the Earth's surface. As I said, as long as the surface is relatively limited, while distortion is not eliminated, it's not too troublesome. But as the area gets larger, it becomes so. The flattening that we see here with the cylinder and the cone is useful in a map projection because, of course, it happens without those tears being too obvious. The right circular cone, if cut up one of its elements that is perpendicular from the base to the apex, can be completely flattened without trouble, and the same can be said of a cylinder cut up perpendicular from base to base. Perhaps more common is a coordinate system, a local coordinate system, that's based upon the idea of a plane, like a flat sheet of paper, being brought tangent to a portion of the Earth, and then a projection of points onto that plane. This is a typical method for local coordinate systems. It's convenient, it's easy, you can satisfy small projects fairly well, and is commonly used in engineering. Now, as long as this section is relatively small, and of course it can be quite small, it can be a particular building footprint, or it can be a lot, or it can be even a relatively larger piece of property. These sorts of local tangent plane have often been used by land surveyors, and they require very little manipulation of any kind to accommodate the fact that the Earth is curved. Of course, the difficulty with this, which is a common difficulty with all plane coordinate systems, is that when these sheets, these planes, are brought together, as you see in this image, they simply don't match. In other words, they overlap, there are gaps, obviously the scale is not the same, so a tangent coordinate system can be useful in a very limited extent as long as one stays within the zone that it intends to cover. When one brings another coordinate system coming from another direction together with it, trouble ensues. So this is, of course, one of the reasons why state plane coordinate systems were devised to cover an entire state or a fairly good portion of a state with a zone, so that one didn't have to cross zone boundaries or go into another system. That is the idea behind state plane coordinates as opposed to local coordinate systems. So even if it was possible to accommodate, let's say, a GIS coordinate system with a local coordinate system, it wouldn't be terribly desirable. Because of the problems of scale and distortion, as mentioned, but also problems of direction. Obviously, north changes as one goes from meridian to meridian around the Earth, and this is an accommodation that has to be made with plane coordinate systems. We'll talk a bit about that. But first, decreasing distortion. This image here on this slide is intended to show how actually the tangent case that we've mentioned contributes a larger area of distortion than does the secant case. The tangent on the left shows a projection plane, flat projection plane, touching the Earth at one point. And this is, of course, what's used actually with polar projections. North Pole, South Pole. And the area in orange shows high distortion. The low distortion, the area in the light beige, is much smaller. However, if one takes the projection plane and cuts the Earth at two places rather than one point, now there's a larger area of relatively low distortion, because you can actually consider it the distance from the points on the Earth to the points on the plane. The less that distance, the less the distortion. And so a secant case has low distortion over a larger area than does the tangent case. This is why state plane coordinate systems in the United States have secant projections. They cut in two places. In the case of Lambert projection, it's two parallels of latitude, and in the case of transverse Mercator, it is two lines that are not exactly meridians, but approximately north-south lines. These are lines of exact scale. But the point is that a secant case projection contributes less distortion than does a tangent lowercase projection. It also becomes apparent that cylinders and cones, these developable surfaces, have the advantage that they're curved as opposed to a flat plane. They're curved in a direction, one direction, so that they can be designed to follow the curvature in the area that's to be mapped. And if a larger portion of the ellipsoid is to be mapped, several cones or cylinders may be used together in the same system to further limit distortion. And that, of course, is how it's done. With state plane coordinate systems, you don't generally have one cone or cylinder that's used for the entire state, but rather a collection of cones or cylinders, one for each zone. And a cylinder or cone defines a zone. That's the approach that was used in the original and current design of state plane coordinate systems in this country. And of course, these are secant projections. They intersect the ellipsoid in two areas. These are lines of exact scale, or standard lines, created along small circles where the cone and the cylinder intersect the ellipsoid. They're called small circles because they don't describe a plane that goes through the center of the Earth, as do the great circles. But where the ellipsoid and the map projection surface touch, there is theoretically no distortion. However, between the standard lines, the map, the plane, the state plane, is under the ellipsoid, and outside of them the map is above it. That means that between the standard lines, a distance from one point to another is actually longer on the ellipsoid than it is on the map. And outside the standard lines, a distance on the ellipsoid is shorter than it is on the map. And any length that's measured along a standard line is the same on the ellipsoid as on the map, and which is why they're called lines of exact scale, or standard parallels in the case of a Lambert projection illustrated up here at the top. Now, this lower picture is a Mercator projection, but not a transverse Mercator projection. To make it transverse, one would turn that cylinder 90 degrees from where it's shown here. This is a standard Mercator projection in this picture. Of course, the overall objective, and it's good to not lose sight of that, the overall objective of state plane coordinate systems is to be able to map each position on the curved surface, the reference ellipsoid, the Earth, to a corresponding position on the surface of the state plane, and then flatten this or develop this state plane surface to accommodate Cartesian or plane coordinates, two-dimensional Cartesian coordinates, x and y, or northing and easting. And you can think of this as being a procedure to move from geographic latitude and longitude to Cartesian coordinates and back again. Now, map projections that preserve the shape of small geometric objects are called conformal, as in Lambert conformal projection, or they're also known as orthomorphic, meaning right shape. In a conformal projection, the angles between intersecting lines and curves retain their original form on the map as what they had on the surface of the Earth. In other words, between short lines, meaning lines under, let's say, 10 miles and 45 degrees on the ellipsoid, would be a 45 degrees on the map. And that the scale is the same in all directions from a point. This is the characteristic. The scale actually is what preserves the angles. Now, on long lines, angles on the ellipsoid are not exactly the same as on the map projection. Nevertheless, the change is small and systematic. There are three projections used in the original state plane. They're all conformal. And all originally were in the North American datum 1927. Now, today, they're actually in North American datum 1983, but originally in AD 27. And there was the oblique Mercator projection in the panhandle of Alaska, and primarily Lambert conformal conic projection and the transverse Mercator projection. Well, here we have a little bit more information on the actual design of the state plane coordinate systems as originally done by Dr. Oscar Adams of the Coast and Geodetic Survey some time ago. The first was done in North Carolina at the request of some highway engineers. Now, Dr. Adams tried to keep the zones that he created to 158 miles approximately. This was to limit the distortion of the lines so that not only were the angles preserved, but there weren't any radical differences in length between a measured line on the Earth and one on the map or in the coordinate system. Now, by not radical, to keep them within 1 part in 10,000, which was pretty good for the surveying technology of the day. He placed 4/6 of the map projection between the standard lines and 1/6 on each side outside at each extremity, as you see in the image here. State plane coordinates were created to be the basis of a method that approximated geodetic accuracy without forcing measurements to be reduced with the rather laborious geodetic calculations that were required. Now, in the days when those calculations required sharp pencils and lots of midnight oil, this was much to be desired, to be able, again, to manipulate large-scale work using plane trigonometry. And, of course, plane coordinate systems can accommodate that, and that was the fundamental idea behind these. The limitation of the zone was to keep the scale distortion to 1 part in 10,000. And this brings us to the scale factor, also known as the K factor and the projection factor. It has lots of names. It's the factor that was originally designed to keep this limit of distortion between, again, what's on the Earth and what's on the map to 1 part in 10,000. These scale factors are therefore ratios and can be used as multipliers to convert ellipsoidal lengths, also known as geodetic distances, to lengths on the map projection surface, which are also known as grid distances. So to convert from geodetic distances to grid distances, and vice versa, you can go the other way too. In other words, the geodetic length of a line on the ellipsoid multiplied by the appropriate scale factor will give you the grid length of that line on the map. Now please notice that I'm talking about the distance on the ellipsoid in reference, not as measured on the surface of the Earth. The scale factor is to move from the ellipsoid to the map and back to the ellipsoid. You can go from grid to geodetic and geodetic to grid. However, there's another factor that we're going to talk about that will get you from the topographic surface of the Earth, where the measurement was made, down to the ellipsoid. But at the moment, we're talking about the scale factor. Now here, in this image, you see a state plane, a grid plane of projection. Here is the horizontal line. And between the standard lines, the scale is too small. And outside, the scale is too large. So a line might be between the bases of those two red arrows on the ellipsoid of reference. It will be projected inward. And as you see, as it's projected inward, the line shortens. That line, B, small b, as you see, will have a scale factor at the K1 position and a scale factor at the K2 position. So to get the scale factor for the line, the approximate method is K, the scale factor, equals K1 plus K2 divided by 2. In other words, an average of those two. Now, if one wanted a precise scale factor, the scale factor equals K1 plus K2 plus 4Km, in other words, 4 times the mean, divided by 6. These are two ways of calculating the scale factor. Generally speaking, the approximate method is certainly adequate, except for very long lines. And a typical state plane coordinate zone, represented by a grid plane of projections cutting through the ellipsoid of reference. As mentioned, between the intersection of standard lines, the grid is under the ellipsoid. There, a distance from one point to another is longer on the ellipsoid than on the grid. That's the plane. This means that right in the middle of a state plane coordinate system zone, the scale is at its minimum. In the middle, a typical minimum state plane coordinate scale factor is not less than 0.9999. Outside of the intersection, the grid's above the ellipsoid, where the distance from one point to another is shorter on the ellipsoid than it is on the grid. There, at the edge of the zone, a maximum typical state plane coordinate system scale factor is generally not more than 1.0001. Now these are the multipliers. These scale factors are the multipliers that one uses to move either from the ellipsoid to the state plane, that's the grid, or you can use the inverse to move from the state plane back to the ellipsoid. Scale factors are for the reduction of lengths. Now, as I mentioned on the previous slide, the scale factor moves us from the ellipsoid down to the projection plane of the state plane. However, of course, we don't make measurements on the ellipsoid, as we discussed last time. Measurements are made on the surface of the Earth. Therefore, if we're going to measure the distance from one point to another, as indicated here, let's say, station Boulder to station Peak, that distance would be measured on the surface of the Earth. Now, we need to have what's known as an elevation factor to move from the surface of the Earth down to the ellipsoid to get that geodetic length. Now, frequently, the way it's done is to get an elevation factor at, let's say, in this case, station Boulder, H1, and get a elevation factor at station Peak, H2, and average the two. That will be your elevation factor. Then that elevation factor is multiplied times the scale factor to give what's known as a combined factor. And then that combined factor is used to go all the way from the topographic surface of the Earth down to the grid. This is one way that distances are reduced to be able to move from the Earth to the state plane. Now you notice in this image that the approximate radius of the Earth, 20,906,000, is shown from the center mass of the Earth up to the ellipsoid. Now, of course, this is an approximation. It's an average. It's a general term. But it's adequate to use in creating this elevation factor. Okay, going over this one more time. Converting a distance measured on the topographic surface to a geodetic distance on the reference ellipsoid. This is done with another ratio that is also used as a multiplier. Originally, this factor had a rather unfortunate name. It was known as the sea level factor back when this was NAD 27. It was given the name because, as you may recall, when NAD 27 was established using the Clark 1866 reference ellipsoid, the distance between the ellipsoid and the geoid was declared to be 0 at Meads Ranch. In other words, the idea was that there was no separation between the two at Meads Ranch. That meant that in the middle of the country, the sea level surface, the geoid, and the ellipsoid were coincident by definition. And since the Clark 1866 ellipsoid fit the U.S. quite well, the separation between the two surfaces, the ellipsoid and the geoid, only grew to about 12 meters anywhere in the country. With such a small distance between them, many practitioners at the time took the view that for all practical purposes, the ellipsoid and the geoid were in the same place. And that place was called sea level. Hence, reducing a distance measured on the surface of the Earth to the ellipsoid was said to be reducing it to sea level. Today, that idea and the name is misleading because, of course, GRS 80 ellipsoid, on which NAD 83 is based, is certainly not the same as mean sea level. And now the separation between the geoid and the ellipsoid can grow as large as negative 53 meters in the coverage of NAD 83. And technology by which the lines are measured has improved dramatically. Notice GPS. Therefore, in the state plane coordinate system 83, the factor for reducing a measured distance to the ellipsoid is known as the ellipsoidal factor, or you can use the name elevation factor, which covers both ideas. Regardless of the name, it's a ratio. And the ratio is the relationship between the approximation of the Earth's radius, that's this 20,906,000 feet, and that same approximation with the mean ellipsoid height of the measured line added to it. Okay. Now that we've talked a little bit about the reduction of a distance measured on the Earth's surface, and there's more information on this, of course, in your reading in basic GIS coordinates. Let's just spend a second looking at directions in state plane coordinates. Now, you will find that every zone in a state plane coordinate system has a central meridian. In Colorado, the central meridian is 105 degrees 30 minutes west longitude, as shown here on this slide. Now here on the left you have station D266, and on the right station Fink. Okay. Now notice in both cases that grid north, this is grid referring to the state plane grid, grid north is exactly parallel with the central meridian, and this of course is the convention for any plane coordinate system. Now that parallelism is convenient because of course therefore on your map in a plane coordinate system north is always up and always the same direction, and all norths are parallel. Of course, on the surface of the Earth, meridians converge at the North Pole. So therefore, there is this value shown here in blue called convergence. That means the difference between geodetic north, that direction along the meridian that would converge at the North Pole, and grid north, this direction that's parallel to the central meridian of the zone. Now, as you see over here on the right at station Fink, it's plus 0.0017.2 seconds. And over here on the left, it's minus, this is west of the central meridian, 0.0040 seconds. All right. Now, as long as one stays in state plane zones and with that parallelism on grid north and so on, you can see that you can have a grid azimuth that is here in red, so that if one occupied station Fink, let's say, on the map at least, and turned the angle 294 degrees, 58 minutes and 50 seconds, that points you down the vector to D266 station. And at D266, using the grid azimuth 650110, that will direct the line to station Fink. And notice that if you add those two red grid azimuths together, as expected, the result is 360 degrees. However, look at the green geodetic azimuths. Now these, of course, are from what we might call true north, or geodetic north, the north that will converge, the north along the meridian that actually goes through the point. Now if one were to occupy station Fink and for example, observe Polaris for an astronomic azimuth, you would turn approximately 294 degrees, 59 minutes, 07.2 seconds. And of course you'll see that the difference there is exactly the same thing as that convergence angle at 17.2 seconds. Same thing over there on D266. You see in the green the geodetic azimuth 65 degrees 00 and 30 seconds differs from the grid azimuth by the convergence in the blue. And one thing you notice immediately is if one were to add the two geodetic azimuths together, they would definitely not add up to 360 degrees. And this is, of course, because on the plane, on the state plane, they have their norths not parallel to the central meridian. So the bottom line is this. On the state plane coordinate grid, north is always parallel with the central meridian, but in reality, at the points on the Earth, north is along the meridian that passes through them, and they are certainly not parallel with one another, and certainly not parallel with the central meridian. Okay, onward to a different plane coordinate system, and this is the universal transverse Mercator system. This is convenient for use over large areas. As you notice, a UTM, or Universal Transverse Mercator Zone, embraces a much larger portion of the Earth than does a state plane coordinate zone. And of course, as expected, when one gets a larger bite, a larger portion of the Earth, the scale factor becomes not nearly so attractive. And you will notice here that it is 4 times less accurate than the typical state plane coordinate system. And UTM has a scale factor that typically reaches 0.9996. Yet, the ease of using UTM makes it very attractive. All NGA topographic maps, USGS quad sheets, aeronautical charts, and so on illustrate UTM grids. It's often said that this is a military system. Several nations, NATO, and many others were involved in its creation to have a consistent coordinate system that could be used by several military organizations from several nations in conjunction so that they were all on the same system. Obviously, that was useful and continues to be useful for UTM coordinates can be used across national boundaries without difficulty. There were conferences held post-World War II, and the UTM system was developed, and it has divided the world into 60 zones that begin at longitude 180. Zone 1, for example, is 180 to 174 degrees west longitude. And the coterminus in the United States, as you see here, is within UTM zones 10 to 18, and I see we have a bit in 19 as well. Now, the UTM system, of course, with 60 zones, means that each zone has a width of 6 degrees of longitude, and they extend from 84 degrees north latitude to 80 degrees south latitude, obviously not covering the polar regions. The south latitude is a small circle that conveniently traverses the oceans well south of Africa, Australia, and South America. However, 80 degrees north latitude was found to exclude parts of Russia and Greenland, and so therefore was extended to 84. Now you notice over here on the right, in this image, you will see letters of the alphabet. C, D, E, F, G, H, no I, because it's too close to 1 and could be confused. J, K, L, M, N, no O, it could be confused for 0. P, Q, R, S, T, U, V, W, X, and no Y, Z. The reason I point this out is because there are GPS systems that use these letter designations along with the number of the UTM zone to identify a particular quad in this picture here. Like, for example, C21 would be the square that you see just immediately above 21 in the southern hemisphere. This is a useful method of referring to a particular quad in a particular UTM zone. and is used also in the military. These zones nearly cover the Earth, as I said, except for the polar regions, which are covered by the Universal Polar Stereographic, or UPS, projection. Now, of course, UTM is founded on a secant transverse Mercator projection, and it's similar to those used in state plane coordinate systems. The central meridian of the zone is exactly in the middle of this 6 degrees, so it would be 3 degrees on each side. For example, that zone I mentioned, 180 to 174 west, the central meridian would be 177 degrees west longitude. Now, the UTM secant projection covers approximately 180 kilometers between the lines of exact scale where the cylinder intersects the ellipsoid. The scale factor grows from 0.9996 along the central meridian of the UTM zone to 1 at the 180 kilometer to the east and west. Now, recall that the state plane coordinates were limited in width to 158 miles. Therefore, they have a smaller range of scale factors, as you would expect. Now, the state plane coordinate factor was designed to not exceed 1 part in 10,000, and the UTM coordinate factor can get as large as 1 part in 2,500. So, as I say, 4 times less accurate with the UTM system. But the convenience of covering a larger area is benefit enough for the change in the scale factor for some applications. Now, on this slide is a recapitulation of what I mentioned concerning the letters on the right side, and as you see, each of these 20 subzones covers 8 degrees of latitude, and they go from C on the south to X on the north, excluding I and O, because they represent 1 and 0 too closely. Now, the development of the UTM grid is defined in meters. Each zone is projected onto the cylinder that is oriented in the same way as is used in transverse Mercator state plane coordinate systems, as we talked about. And the radius of the cylinder is chosen to keep the scale errors within acceptable limits. And here we have an illustration of a typical UTM zone. Now, you notice over here on the left, the equator is, of course, the division between the north UTM and the south UTM. And, of course, when one designates a letter, you have to designate whether you're talking about north or south. The scale increases as you move outside of the standard lines, and it decreases as you move into the middle. The CM here is indicated as the central meridian. AB and DE are the lines of intersection of exact scale. And then, of course, over here on the right we have an image of the Earth inside a transverse Mercator developable right circular cylinder. Unlike any of the systems previously discussed, every coordinate in UTM zone occurs twice, once in the northern hemisphere and once in the southern hemisphere. This is a consequence of the fact that there are 2 origins in each UTM zone. This is, of course, quite different from state plane coordinates. The origin for the portion of the zone north of the equator is moved 500 kilometers west of the intersection of the zone central meridian and the equator. This arrangement ensures that all of the coordinates for that zone in the northern hemisphere will be positive. Now, the origin for the coordinates in the southern hemisphere for the same zone is 500 kilometers west of the central meridian too. But in the southern hemisphere, the origin is not on the equator. It's 10,000 kilometers south of it, close to the South Pole. This orientation of the origin guarantees that all the coordinates in the southern hemisphere are in the first quadrant and positive. In other words, the intersection of each zone's central meridian with the equator defines its origin of the coordinates. In the southern hemisphere, each origin is given the coordinates easting 5,000 meters and northing 10,000 meters. In the northern hemisphere, the values are easting 5,000 meters and northing 0 meters at the origin. So the idea is that there are two origins, one for the northern hemisphere and one for the southern hemisphere in each universal transverse Mercator zone. Okay, that's the discussion of plane coordinates for this lesson. And as I say, there is much more to know concerning them. I've tried to give a taste of some of the elements of plane coordinates. This, of course, is not a course primarily on plane coordinates. The reason that I have delved into it is because of the normal usage of them in GIS work and GPS as well. There's much more information in the Basic GIS Coordinates book, and I welcome you reading more about it. Anything, questions that arise, please don't hesitate to ask. Now, moving on to heights. As you know, in a normal course of things, a coordinate, xy or northern, easting, or latitude and longitude, is not fully a definition of a position. Now, we've discussed also Earth-centered, Earth-fixed XYZ coordinates, but normal course of things, a horizontal coordinate is given, and a height, or also known as an elevation. This third element, known also as elevation, was originally, in most cases, determined by spirit leveling, or in some cases, what's known as trigonometric leveling, turning vertical angles optically. But whatever method was used in the past, it was based on optical instruments oriented to gravity, therefore oriented to the geoid, and the elevations, or the heights that were derived, were orthometric, based upon gravity. So we have a long legacy of benchmarks and recorded heights and archives that are based upon this sort of methodology of determining heights. And so this is what we normally think of when we talk about elevations. We think of orthometric, or heights based upon gravity. However, there's another kind of height, and that height is an ellipsoidal height. This is the vertical distance from the ellipsoid. This is that mathematical model of the Earth up to a point that actually is on the Earth's surface. Now here in this image we see an ellipsoidal height, which is also known as a geodetic height, of small h, is the way it's symbolized, plus 2644 meters. Modern geodetic datums rely on these geocentric ellipsoids that we've talked about last lesson to approximate the surface of the Earth. And of course the actual Earth does not coincide with these nice smooth surfaces. Abstract points may be on the ellipsoid, but the physical features of those coordinates are on the Earth, or on the topographic surface of the Earth, and therefore the intention is for the Earth and the ellipsoid to have the same center. And the surfaces of the two figures are certainly not in the same place. There's this distance between them, and that's this ellipsoidal height we're looking at. The distance represented by a coordinate pair on a reference ellipsoid to a point on the Earth's surface is measured along a line perpendicular to the ellipsoid. Remember that from last lesson. This is a different direction than the direction of gravity, perpendicular to the ellipsoid. This distance is known by more than one name, but ellipsoidal height is generally what I will use, and it is symbolized typically by small h. Now here we have an image that we looked at last time of an instrument level on the topographic surface of the Earth, and of course the direction of gravity does not coincide with perpendicular to the ellipsoid. Ellipsoid height of a station is illustrated here. And the concept's very straightforward, of course. A reference ellipsoid, however, may be above or below the surface of the Earth at a particular place. If the ellipsoid surface is below the surface of the Earth at a point, the ellipsoid height has a positive sign, as you see here in this image. If the ellipsoid surface is above the surface of the Earth at a point, the ellipsoid height has a negative sign. That's important to remember. But it's also important to remember that the measurement of an ellipsoid height is along a line perpendicular to the ellipsoid and not along a plumb line. And most often these are not the same. And of course, it's worthwhile to also remember that it's completely impossible to set up any instrument, including a GPS receiver, on the ellipsoid, since the ellipsoid is an abstract, imaginary thing. So, the point is that ellipsoid heights are not what most people think of as an elevation. That's different. That's an orthometric height based upon gravity. An ellipsoid height is also not measured in the direction of gravity, and it's not measured, therefore, in the conventional sense of down or up. Now you may wonder, why in the world spend any time at all on this bizarre idea of an ellipsoid height? Since you can't measure it directly, you can't set up on the ellipsoid, what's the point? Well, here's the point. As you see in this image that we saw last time, the ellipsoid height, not the orthometric height, is what is determined directly from a GPS measurement, not orthometric, ellipsoidal height. And of course the reason is relatively straightforward again. The satellites that are the GPS satellites orbit around the center of mass of the Earth. They have no concept of where the surface of the Earth is. Your receiver, which is on the surface of the Earth, of course, could just as well be in outer space as far as the GPS coordinate, or centered Earth fixed XYZ, is concerned. Now, from that XYZ, of course, it is certainly possible for your GPS receiver to calculate a latitude and a longitude given a particular ellipsoid, but that ellipsoid is what it will base those latitudes and longitudes upon in its microcomputer. And of course the height that is determined up to the station that you're interested in will also be based upon the ellipsoid. So the ellipsoid height is what comes out of a GPS receiver, and the reason for that is, of course, it's difficult for it to know where the surface of the Earth is. Now it's worthwhile to note, as we noted about latitudes and longitudes, that ellipsoid heights vary as the ellipsoid changes. As the datum changes, the ellipsoid height changes, and that's what this image here is intended to represent. There's a approximately 2.24 meter separation between the origin of NAD 83, the GRS 80 ellipsoid, and the ITRF ellipsoid. And because of that difference, then the heights, the small h, the ellipsoid height derived from each of these, would be slightly different. And of course, again, remember that a coordinate, a latitude and longitude, a northing and easting, an x and y, and even a height, is dependent upon the type of datum that you're using. It must be specified for the coordinate to make any sense. Now, any object in the Earth's gravitational field has potential energy, because of course it's being pulled toward the Earth. Now, quantifying this potential energy is one way to talk about height, because the amount of the potential energy an object derives from the force of gravity is related to its height. As we remember, when J. Richter was approaching the equator, Newton derived his theory that there was more Earth under the equator as he approached it, 17 miles as I recall, because of the difference in the gravitational force. Now, an equipotential surface is a surface that is connecting points of equal gravity. The geoid is the particular equipotential surface that has been chosen to represent something that is closest to mean sea level. Of course, we can't use sea level exactly, because temperature, salinity, currents, winds, etc. affect it. But the geoid, defined by gravity alone, is a particular equipotential surface arranged to fit mean sea level. And as you see in this image, the geoid and the ellipsoid are not the same. Now, of course, remember that the legacy heights determined by optical instruments in the past were always relative to the geoid, because, of course, the instruments were oriented to gravity. However, GPS heights are related directly, at least, to the ellipsoid, two different surfaces. So, well, there is a relationship between mean sea level and the geoid. They're not the same. They could be the same if the oceans would hold still, but of course they won't. And so therefore, the deviation between, and we saw this image last time, the geoid's not smooth and continuous, it's lumpy because gravity is not consistent across the Earth. And at every point gravity has a magnitude and direction. A vector can describe gravity, but these vectors do not have the same direction or magnitude. Some parts of the Earth are denser than others. Where the Earth is denser, there's more gravity, and the fact that the Earth is not a sphere also affects the gravity. So it follows that defining the geoid precisely, actually measuring the direction and magnitude of gravity in many places, is what needs to be done, and has been done. The geoid undulates with uneven distribution of the mass of the Earth. It has all the irregularity you would expect. And therefore, the separation between the lumpy surface of the geoid and the GRS-80 ellipsoid worldwide varies from plus 85 meters west of Ireland to about negative 106 meters in the area south of India, near Ceylon. This is where you see this large blue area. Now in the coterminous United States, this variation is from negative 8 meters to negative 53 meters. But even these small distances are large and larger than that was under the old NAD 27. Because remember, under that system, the variation was only 12 meters. However, NAD 83 is based on GRS 80, and the difference between the ellipsoid and the geoid can be large. Okay, so here's the way we proceed with GPS. A geoid height is the distance measured along a line perpendicular to the ellipsoid of reference to the geoid. Also, as you can see, these geoid heights are negative. They're symbolized by large N. If the geoid's above the ellipsoid, N is positive. If the geoid's below the ellipsoid, N is negative. It's negative here because the geoid's underneath the ellipsoid throughout the coterminous US. Now recall that the ellipsoid height symbolized h, small h. Ellipsoid height's also measured along a line perpendicular to the ellipsoid of reference, but to a point on the surface of the Earth. You see that here in the black arrow. However, the orthometric height, which is what we want, is symbolized by large h, and it's measured along a plumb line from the geoid to the point on the Earth's surface. So you can calculate h, large h, the orthometric height, what you want. It equals ellipsoidal height minus geoid height, or that separation between the ellipsoid and the geoid. And this is the way it can be converted. So when a GPS receiver provides you with an ellipsoidal height, what you do is you subtract the separation between the ellipsoid and the geoid at that point, and presto, you have the orthometric height, the objective. Now this is done in some cases automatically by a GPS receiver. However, what it must have to do this is a geoidal model loaded into its circuits to do this calculation that we see right here. And this is typically available. Fortunately, NGS has provided us with ever better geoidal models. Major improvements have been made over the past quarter century in mapping the geoid, both on national and global scales. We had the Geoid 90 model. Again, these were available from the National Geodetic Survey. We've got the Geoid 99 model that covers the coterminous U.S., Virgin Islands, Puerto Rico, Hawaii, Alaska. The grid is 1 degree by 1 degree. And here's a little quote from NGS. When comparing the Geoid 99 model with GPS ellipsoidal heights in the NAD83 reference frame and leveling in the NAVD88 datum, it is seen that Geoid 99 has roughly 4.6 centimeter absolute accuracy in the region of GPS on benchmark coverage. In those states with sparse GPS benchmark coverage, less point accuracy may be evident. And then, of course, Geoid 03 has superseded the previous models in the continental U.S. And improvements will undoubtedly continue. The point of the discussion being that you need a geoidal model to convert a GPS height into an orthometric height. Thank you for spending this time with me, and we will proceed with Lesson 7 next.